Welcome to solverfy.
In this question, we're given the absorption spectrum of this iron complex containing 5 water ligands and 1 thiocyanate ligand. First, we want to know the color of the solution of this complex. And for that, we need to look at the spectrum and notice that the maximum absorption takes place right here in what seems to be the green region of the electromagnetic spectrum. So remember that this is an absorption spectrum. So if we are absorbing green light, what light are we transmitting? To figure that out, we need to take a look at our color wheel. So what we are seeing is green light. That means that the complementary color, which is the light that is, forgive me, I got that backwards. We're absorbing green light, which means that the color that we are seeing is the complementary color, and that is red. So the solution of the cyanotic complex is red. Next, in part B, we are asked to calculate the crystal field splitting energy in kilojoules per mole. For that, we need to look at the absorption spectrum again and notice that this maximum absorption takes place around 480 nanometers. We're going to use that information to calculate the crystal field splitting energy using the equation. Delta is equal to Planck's constant times the speed of light divided by the wavelength. So remember that Planck's constant is 6.626 times 10 to the negative 34 joules seconds. The speed of light is 3 times 10 to the 8 meters per second. And then remember that we said that the wavelength was 480 nanometers, but the units that we need here are meters. So instead of nanometers, I'm going to use 10 to the negative 9 because 1 nanometer is equal to 10 to the 9 meters. So notice that change in units that happens down there. Do a quick unit check. My meters will go away, my seconds will go away. I will be left with units of joules, which is units of energy. And this is equal to 4.14 times 10 to the negative 19 joules. Now that might seem like a really small number, and that's because it is. This is a very small amount of energy needed for the D to D transition of a single ion. So for one ion, this is the crystal field splitting energy. But we were asked for the energy in kilojoules per mole. So we're going to need to convert this energy for one ion using first Avogadro's number, 6.02 times 10 to the 23rd, because there's that many ions in 1 mole of ions. And then I need units of kilojoules. Kilo means 1,000. 1 kilojoule contains 1,000 joules. Now check your units one more time. We've got joules, joules, ions, and ions. So the units we're left with is kilojoules divided by moles. And that value is equal to 249 kilojoules for every 1 mole. Next, we are told in part In part C, we're told that the hexa-aqua iron complex is a pale violet solution, and we want to compare its crystal field splitting energy to that of the thiocyanate complex. To do that, let's go back and look at our color wheel from part A, which looks like this. Recall that the thiocyanate complex was red, and that meant that the green light was absorbed. We saw that in the absorption spectrum. And now we're being told that the hexa-aqua complex has this pale violet solution. So this is the hexa-aqua complex. If this complex is pale violet, then that means that the light absorbed by this complex is yellow. Okay, so these two go together. Okay, but we're being asked about the crystal field splitting energy. Remember that the absorption, the energy that's absorbed, is equal to the crystal field splitting energy. That's the energy of light that is absorbed by the electron to do that D to D transition. So we need to compare the energies of the green and yellow light. And you should know that red light has the lowest energy, violet light has the highest energy. So as we move kind of clockwise around this color wheel, we're moving to higher energy. Okay. That means that green light has greater energy than yellow light. And if that's the case, the cyanate complex is going to have greater crystal field splitting energy than the all water complex. So to answer the original question, the crystal field splitting energy of the hexa-aqua complex is smaller than that of the penta-aqua thiocyanate complex. Next, we're asked, given the information we found in PNC, we need to compare the field strength of the two ligands, of the water ligand and the thiocyanate ligand. For that, we need our spectrochemical series, or it would be helpful to have our spectrochemical series, which orders ligands according to their ability to split the orbitals. So we see that large crystal field splitting corresponds with strong field ligands, while small crystal field splitting corresponds to weak field ligands. So the ligands that we are comparing are water and thiocyanate. And what we saw in parts B and C above is that the more water you have, so here we go, the more water you have, the lower the energy of the absorption. I'll say that again. The more water you have, 6 water ligands compared to 5, the lower the energy of the absorption. Put another way, put another way, replacing a water with a thiocyanate ligand increases the absorption. So, and that seems to suggest the thiocyanate has a greater crystal field splitting energy compared to water. Okay, so let's go back and say that again. So it seems that replacing water with thiocyanate results in greater crystal fields, greater absorptions, greater energy absorption. And greater energy absorption corresponds to greater splitting of the d orbitals. Let's look at a quick picture of that. If it takes more energy to cause an electron to jump from the lower energy to the higher energy, then that means that the crystal field splitting energy has increased. So it seems that thiocyanate is the stronger field ligand. So it has the stronger crystal field strength, or the greater, I should say. And finally, we are told that this other complex, this hexacyanado complex, is red in color, and we're asked to compare its crystal field spreading energy to that of the thiocyanado complex. And for that, again, I will bring back our color wheel. We know from earlier that this thiocyanate complex is also red. So both of these appear the same color. That means they must absorb the same or similar wavelengths of light. So if they have the same color, they have similar absorption. And if they have similar absorption, they must have similar crystal field splitting energies. So